Welcome everybody on the AP Chemistry series. Today we will start with Unit 7, so let's hit it up. We just want to tell you a story about today's experiment. The scientists just grouped amount of reactants of carbon monoxide with water, just like they mix them since they're in gaseous in a closed system right here. So as the reaction starts to proceed, like the products will be formed. So you can see that in B, we have some products that are formed and they're represented in terms of CO2, like this one here. Like we have so many CO2, in addition to the hydrogen gas that is also produced in here. So as the reaction proceeds, the scientists, as a result of looking at the reaction, when the scientists look at the reaction, okay, they just thought that the reaction has stopped and they were so happy. But after checking the reaction, like in C and D in here, they just found something weird. They found reactant, the CO carbon monoxide, and they also found a reactant of water. They also found some products that are formed. So, like, we're supposed to have reaction that starts with reactants and ended up with the products. But at that point, we have products and reactants at the same time. So what happened? The scientists just like conducted so many investigations and they just concluded something. The reaction has reached to the equilibrium. So where's the meaning of equilibrium at that point? The equilibrium says it's a state at which the rate at which the reactants are consumed to form a products, it's the same as rate when the products are turned to reactants. In other words, the rate of the forward reaction is the same as the rate of the backward reaction. So the formation of a products is the same as the consumption of reactants. The result of this process, if you look at the two figures in C and D, if we start counting the numbers of carbon monoxide CO, let's just count them in here. This is one, okay, and this is two. So we have two carbon monoxide, okay, in C. We have um, how many water molecules? We have one water molecule, two. Okay, so we have two water molecules. If we count the number of CO2 at that point, we have one, two, three, four, five. Okay, so we have five carbon dioxide. And what about the H2? We have one, two, three, four, five. So for C, we just noticed that we have two molecules of carbon monoxide, two molecules of water, five of CO2, and five of H2. Now, if we count the number of molecules in D in here, we have one CO, we have one, then you have two. What about the water molecules? We have one water molecule and we have two molecules. What about the CO2? We have one, two, three, four, and five. So we have five molecules of CO2, and the last reactant is the H2. And here we have one, two, three, four, five. So at that point, you can see that from C to D, that we have a fixed component of products and reactants. The products have a constant concentration or constant number of particles. And if you look at the same thing for the products in C, and the same thing is repeated with CO and water in here and seawater in here. So what do we conclude at that point? We just conclude something that the concentration of the products and reactants do not change. And since you're in equilibrium state, then the rate of the forward reaction is going to be the same as the rate of the reverse reaction. Let's study this type of reactions in here. Focus on it. Okay, first of all, we have two reactants. We have nitrogen gas and hydrogen. the product is ammonia or NH3. So since we're in equilibrium, it means that the consumption of the reactant rate is the same as the changing of a product into reactants. They have the same speed. And that's why the concentration of NH3 becomes constant, and the concentration of N2 and H2 is also constant. Let's just think about if we start with a concentration. Let's just like an example. If we start with 1 here and 2 for hydrogen. As we know that since they are not reacting so far with each other, the initial concentration of NH3 is 0 since we don't have a product so far. So we can represent the 2 in 1 as initial concentration. So I can represent the 2 to be in here and the 1 to be in here. Okay. What happened to the concentration of reactants as the reaction proceeds? The concentration of reactants start to decrease, and that's why it's represented in the graph. They are decreasing, you can see. Okay, but my question, which of these two reactants, hydrogen or nitrogen, has a higher disappearance rate? Since like the graph represents concentration versus time, so we're measuring the change in concentration over a unit of time. So which of these represents a higher rate of disappearance since they start to disappear? If you look at the hydrogen and the nitrogen, you can see that the hydrogen is steeper. Okay, this is steeper than the nitrogen. The steepness tells me that the disappearance rate of hydrogen is higher than the disappearance rate of nitrogen. And there is a reason for that? Sure, there is a reason. If we go to the equation right here, you can see that the rate of disappearance of hydrogen is greater than the nitrogen. The hydrogen is greater than the nitrogen because the hydrogen is multiplied by 3. So the coefficient is higher than the coefficient of N2. And that's why it decreases faster than the nitrogen. Okay. Now, since the concentration of reactants start to decrease as the reaction proceeds, the concentration of a product will decrease. And it's represented in here. It will start from 0 because it wasn't ammonia, like we didn't have ammonia so far, and it don't start to increase. Ammonia started from 0 and then it started to increase at that point. All right. Is there anything to discuss about that? Where is the equilibrium area? Okay, as we said from here, the concentration of products and reactants do not change. It means that they will be fixed, right? So how is that reflected in this graph in here? You can see that the reaction has a flat line after a certain period of time, flat line with NH3 and a flat line at N2 at a certain time. So what is the reason why? What does this represent? The flat line tells me that the reaction has reached to the equilibrium. What does it mean? It means if you want to read the y-axis reading for the hydrogen, you have to extrapolate it and just read this value, which means it's a fixed number. If you want to read the concentration of ammonia, you have to take a vertical line and extrapolate it and just take this number in here. And the same thing for the N2 in here. So since you have a fixed concentrations, it means that the reaction has reached to the equilibrium. Recall everything in here. All right, first of all, we have two reactants. You have H2 and N2. They are decreasing. They were in higher concentration, then they start to decrease. The hydrogen decreases faster than the nitrogen because it has higher coefficient, and that's why it disappears in a faster rate. And for the NH3, it's a product that starts from 0 and then it starts to increase. The flat line represents the equilibrium thing. And I can ask you, what is the time at which the reaction has reached to the equilibrium? And you can say, okay, when does it become flat? It becomes in here. Then this is the T equilibrium at which it started to be in equilibrium. Thank you.